So the first session is on non-line of sight imaging. There are 3 papers that covers various aspects of this problem. But since it's the first session, let me just go over some of the details. Each talk is 20 minutes long, with 17 minutes for the presenter and 3 minutes for a Q&A session. There are mics. There's a mic right there, and I'll have a mic in my hand. So feel free to come forward, either grab it from my hand or speak your question in there. We are ready to start whenever you are. Oh, you're ready. Okay. So the first, I was hoping to use your slide to introduce yourself, but that's good. The first talk is called Thermal Non-Line of Sight Imaging. The authors are Tomo Maeda, Yichin Wang, Achyuta Kadambi, and Ramesh Raskar. The authors are from MIT Media Labs and UCLA. Tomo and Yichin will be presenting. Take it.
Hello, my name is Yichin Wang. We're going to do something different. We start with a weird white blank slide. This is actually the slide. I'm going to ask you to consider one scenario. I will ask my colleague, Tomo, to hide from me. Now, how can we create a camera that can see Tomo's pose in real time? Seems like a hard problem. But let's break it down. What is the main difference between Tomo and what he's doing here? What makes him special? Let me ask you this question. Is it motion? Let me actually check with my line of sight eyes. See, no, he's steady. He's static. Is it color? Well, there are similar colors, maybe showing in the same position, like he's wearing dark color pants, and the background is also dark color. So let me ask you the question, what actually makes him special? I'm going to give you my answer. The answer is heat. Tomo is hot. Well, at least he is hotter than the background. Maybe we can use thermal cameras to see around corners. So let's see how that looks. Here we have a person hidden around the corner, and we are looking at the wall. What we get? High quality pose estimation of occluded person. And now we present thermal non-line of sight imaging. Along with my co-authors, Tomo Maeda, and our faculty advisors, Ramesh and Achyuta, we exploit the unique physics of thermal reflections. As everyone here may know, non-line of sight imaging, also known as seeing around corners, has gained significant interests during recent years. The ability to look around corners has applications that span from huge social impacts, such as searching and rescuing operations, to daily applications, such as autonomous vehicle navigation, or just simply to see if your coworker is bringing you coffee without leaving your chair. So non-line of sight imaging was first demonstrated with a time-of-flight camera. Let us describe how this field of imaging has been advanced. Time-of-flight gives the distance constraints on the hidden objects and are useful for non-line of sight imaging. Because of this advantage, a lot of work in this field use time-of-flight camera to see around corners. Another method is to use coherence properties of light to perform non-line of sight imaging. For example, some works use speckle patterns and spatial coherence to perform tasks such as tracking and localization. Finally, we can use traditional cameras capturing the intensity information to see around corners. This approach uses shadows casted by occlusions to gain information about the objects around corners. In other words, the quality of intensity measurement-based techniques heavily depend on occluding geometries. Our technique is intensity measurement-based, but do not require any occluding geometries. Moreover, while most of past works assumed Lambertian reflections, our model incorporates more complex BRDF for long-wave IR. In the past, specular reflection was used in time-of-flight-based technique. We will extend it to the intensity-based method. Let me show you what we can do with our technique. First, we demonstrate 2D shape recovery and 3D localization with intensity-only measurements. Note that while previous passive reconstruction technique based on intensity measurements requires occlusions, ours does not require such geometry. Second, we perform near real-time post-estimation of a person around corners as we discussed. The result shows the potential to the actual real-time application of non-LSI imaging. Main uniqueness of our approach is the use of long-wave IR. Previous works on non-LSI imaging used visible lights or near IR. We use wavelengths between 8 micrometers to 14 micrometers. From now on, I will pass this presentation to my co-author Tomo from Boston for more details of how we exploit unique properties of long-wave IR for non-LSI imaging.
So what is the difference between the long-wave IR or visible light in non-LSI imaging setup? In the visible range spectrum, an object acts as a light reflector, so the signal comes from 2 bound photons. The ambient light source emits photons. Some of them hit the target, scatter at the wall before reaching the camera. Moreover, most of the photons you capture is a single bounce photon from ambient light source, and it doesn't contain any signals about the information about the target. This makes signal-to-noise ratio extremely small for intensity-based measurement in the visible range. Long-wave IR has different light transport model. First, any heat source acts as a light source, so the signal comes from a single bounce photons that are directly emitted by the target. The second, the surface reflection is much more specular than the visible range because of the long wavelengths. As a result, the 2D shape of the object becomes visible and easy to recover. These unique properties of the long-wave IR is extremely useful for non-LSI imaging in some setting. Now let me describe how we model the target as a light source. Stefan Boltzmann law relates the temperature of the black body and the long-wave IR radiation. Including an emissivity term, if we know the temperature and emissivity of the object, we can estimate the radiance of the hidden light source. With the background subtraction of the ambient temperature, we can treat the object with a long-wave IR radiance shown on the slide in the equation. After translating the thermal measurement into intensity information, we can actually use the optical light transport to model the mapping between the object and the measurement. We need BRDF to model this. BRDF describes how the light reflects off the surface. It typically consists of 2 terms, diffuse and specular. Diffuse reflection is a random scattering that sends the photon all over the angles uniformly. The specular reflection is more like a mirror-like reflection with some angle width. The strength of these 2 terms depends on the wavelengths of the light and the roughness of the surface. With long-wave IR, the wavelengths becomes longer than the roughness, and the specular reflection dominates the surface reflection. We actually capture the surface reflectance of some materials and see that the diffuse reflection can be ignored or is negligible for different types of surfaces. From these observations, we use specular BRDF model to capture the surface reflectance. Specifically, we use Cook-Torrance model with GGX surface normal distribution. I won't go into the details, but the model consists of 3 terms that depends on a single parameter, alpha, that represent the roughness of the surface. With this, we have a very simple representation of the surface reflectance, and we can model the mapping between the measurement to the object to the measurement. Note that the albedo is outside of BRDF and has to be separately estimated. Incorporating the BRDF and long-wave IR radiation, we can write the intensity of the camera pixel measurement as an integral over 3 terms. The first is over the surface of the object. The second is over the area of the wall corresponding to the camera pixel. And the third is over all the direction of the reflected light path that intersects with the camera. If we have a Lambertian surface reflection, then we have closed form for this. However, because the model is complicated, we use Monte Carlo method to approximate this integral. Specifically, we use Mitsuba renderer that incorporates the BRDF model and Monte Carlo path tracer. Now we have provided a background on non-line side imaging with thermal camera. Now we will overview the techniques that we developed. First, let me illustrate the passive localization and 2D shape reconstruction. Since the reflection is very specular, as I explained, we get the images measurement where we can already see the 2D shape. So we can simply apply thresholding to recover the 2D shape of the object. Yes, it's trivial to recover the 2D shape of the object, but the 3D localization is not. Given the 2D shape, there's ambiguity between the size and the depth of the object. The object can be close to the wall and small, or far away from the wall and large, to produce the same 2D shape in the reflection. We resolve this ambiguity using the intensity information. Because the surface reflectance is not perfect mirror-like reflection, the intensity drops as the object moves farther away from the wall. This phenomenon can be captured using our BRDF light transport model with specular BRDF. So first, we need to capture the BRDF of the surface to use this model. Let me illustrate some of the example of how we can capture this, the BRDF. The first is simply rotate the surface with fixed point source and camera. Or you can, for fixed surfaces, you can move around the camera and the light source. Or more simple, there's a more simple way with known heat source at known locations. And we can simulate the exact same scene as simulation and tweak the parameter of the surface reflection so that the simulated result matches with the measurement. In this paper, we use the setup on the left to get an accurate estimation with the roughness parameter alpha, and setup on the right, the simpler setup to estimate the albedo of the wall. Once we estimate the BRDF and the long wave radiation from the temperature prior, we simulate the scene with different size and depth combinations from the 2D shape recovery. Then we find the best matching a size and depth combination that best fits the actual measurement and the temperature prior. Let me give you an intuition behind how this actually works. So the 2D shape, the size and depth ambiguity from the 2D shape depends on the total distance from the camera to the wall and from the wall to the object. On the other hand, intensity information, which depends on the surface reflectance, depends only on the distance between the wall and the target. So we have 2 different constraints for 2 unknowns. And using these 2 constraints, we can resolve this ambiguity. Here's an example of 3D localization and the 2D shape reconstruction results. As you see in the left A, we really cannot see the hidden object in the visible spectrum. However, if you capture the right BRDF parameter, then we can estimate the location of the object successfully, as shown in the figure C on the right. Please see our paper for more results with different types of surfaces. Now, Yuqin will describe how we achieve robust pose estimation around corners.
So, the specular dominant reflection of long-wave IR is favorable for computer vision applications in the corner setting. Here, we pick an important application, pose estimation around the corner. We used a whiteboard as corner wall. The camera is looking at the whiteboard, and the person, in this case, myself, is not directly seen from the camera. As you can see, the camera successfully recognized me as I walked into the scene from the right and performed some gestures. As you can see on the left, a traditional pose estimation algorithm, in this case, Young-Ramanan, fails with non-left-side thermal images. Incorporating our insight of long-wave IR light transport, we used denoisers to preserve some important features to make pose estimation robust. Here is a comparison of the same clip before and after denoiser. The left one is raw data. The middle one passed through a medium filter. The right one passed through total variation denoiser. In addition, because pose estimation is a score-based algorithm, we can use thresholding on the scores for human detection. As you see on the right, we can set an appropriate threshold to see if the person is actually in the frame or not. Now, I will pass back to Tomo.
And of course, there are limitations to thermal non-linear imaging, just like all the other methods. First, the object type is limited to heat cells, so we may see the person around the corner, but may not see the statues. Also, our localization method have other assumptions such as single depth or uniform temperature. We hope that these assumptions can be relaxed in the future works. The second, we observed that some of the material exhibit extremely low albedo, making the signal-to-noise ratio really small. To tackle these issues, we may want a better denoising algorithm for specifically for thermal images, or simply the better sensors. So non-linear imaging is very challenging, as you may know, and there might not be a solution that solves all the scenarios. I think for localizing or seeing the heat source around the corners, if the target emits some heat and long wave IR, using the thermal camera might be the solution to non-linear imaging. As we show in this presentation, there are unique physics around long wave IR that is extremely favorable for us to see around corners in some scenarios. We hope that this work inspires the advances on the non-linear imaging by exploiting these unique properties of long wave IR. We are also going to be presenting at the poster session today, and happy to discuss further details in person. Thank you very much. So for that's a good question. So for the localization, we need to know the location of the wall, so like the scene geometry, like the line of sight scene geometries. And we just manually calibrate it because it's, I know it's a hard problem to solve in practice, but it's easier problem to do to recover the scene and line of sight. Also, it's quite sensitive with the BRDF estimation. So this step has to be so right now, the BRDF estimation takes a little bit of time, or good like resolution on that, like spatial resolution of the like mechanics to get the BRDF. So this problem has to be solved. But on the other hand, pulse estimation doesn't require any of this intensity information. It just needs the shapes. So for those, we don't really need the calibrations. Oh, okay. So the thermal sensors. We use the flares like Lepton 3, and we can turn off the calibration sets, like the thermal cameras like calibrate every once in a while. We can turn off the setup, and I didn't see any deviations from the original. Like it's consistent.
Ambient thermal lights or your signal lights. How is that the signal to noise ratio affects your performance?
Okay. So for long wave IR in this long wave IR spectrum, there's no basically for example, in the visible spectrum, you have the sun or room light that acts as ambient light, and a lot of things that I see from the wall is coming from that and the single bounce, and some of the photons hit you and comes, and it's extremely challenging to resolve these things. But for in this room, the long wave IR sources are like typically human body, and maybe the projector and some of the light. But because the reflection is very specular, it's like you have the very unique angle matching between the object and the wall point. So in general, we use the room light for our experiment, and we didn't really see any effect of ambient light.
Assuming stereo, you mean using two thermal cameras at the same time to implement the performance of yes. That's actually a very good point. I mean, based on our experiment, we only use one, but later on we can expand it to using multiple ones at the same time to see if we can improve any of the applications or even improve the entire performance of that. Sure. Yeah, we would.